So let us begin. We are continuing studying different methods of data analysis. And today we will discuss a new topic that is called clustering. And this is the topic that is somewhat related to an idea that you have some data, and this data is naturally grouped, but you don't know the grouping, and you want to uncover it in some way. So, for example, assume that you have two numeric variables in your data. You have x1 and you have x2. And your data looks like the following. Something like this. And just by looking at this picture, you can see that there are three groups, and you can distinguish between them. You can say that this is one group, and this is another group, and this is the third group. And so we can do it just by visual inspection of this picture. But sometimes we need to do this grouping in some way automatically. Because, for example, we assume that there is some clusters in our data, but we don't know for each point, for each observation, we don't know in advance to which cluster this point belongs. Probably we just don't have enough data. For example, we have, I don't know, assume that we have some people who use some website, and we have statistics about how these people behave. And we believe that these people should be grouped naturally into several groups which are close to each other. So we believe that there are groups such that inside each group, people are similar to each other, but groups are different to each other. So, for example, we can expect that males and females will work with our website in somewhat different ways, but we don't know in advance how. So we can use these clustering algorithms to get some answers. Unfortunately, this clustering problem is not so well posed, well defined. If we compare this problem with other problems like that we solved in regressions. In regression, everything is simple. We have some value that we want to predict. We have some variables that can be used to predict, and we want to create some function like linear function or more complex function. And in a sense, we already have correct answers in our data. We have already some values that are the values that we want to predict. Clustering is related to a kind of unsupervised learning models, and in these models you don't have correct answers in advance. So you just want to uncover some structure in data, but in any case, it is not clear is your result correct or not. But anyway, sometimes they are useful. And so let us discuss some popular clustering algorithms. Okay. First of all, before we continue with algorithms, we have to discuss a little bit the notion of distance between our data point, because if we try to formalize the clustering problem, we have to say something like this. Well, why do we believe that these points belong to the same cluster? And for example, these points, these points and these points belong to different clusters. Why do we believe that this is correct? How we find these clusters by visual inspection? What makes these clusters so visible? And if we are trying to answer this question, we see that the idea of this clustering, at least on this picture, is that points inside this cluster are close to each other. And if I took 2 points in different clusters, they are far from each other, at least comparing to these distances. So this is our idea. If we want this kind of compact clustering, this is not the only possible way to define it, but at least if we want it, then we need something like so if we want compact clusters, we need we have to minimize distances between points in the same cluster. So I can pick 2 points in the same cluster, in this cluster, or in this cluster, or in this cluster. And I want that the distance between these points be as small as possible. I can find, for example, average distance or sum of all distances or sum of their squares. But anyway, the idea is that these things should be small. The size of clusters should be small. And distance between clusters should be large. So to proceed, we have to discuss this notion of distance between different points, distance between different data points. Actually, it is not as straightforward as it is on this picture, because basically we don't have any canonical distance in the spaces that we are working with. For example, assume that I have 4 points that are located in this way. How would you cluster these 4 points? Let me enumerate them. 1, 2, 3, 4. What is the natural clustering of these 4 points from your point of view?
By pairs, 2 and 3 and 1 and 4.
Yeah, 1 and 4 and 2 and 3. This is one cluster, and this is another cluster. Okay. Now let me assume that this data are, for example, related to some, I don't know, some properties of people and some sounds that they produce, and assume that x1 axis is h, and initially this h is, I don't know, h in centuries. Okay, nobody actually measures age of people in centuries, but let us assume. And x2 will be another value, for example, some duration of some sound. I don't know what is this sound, and this duration is measured in, for example, milliseconds. And so we have one here, 1, 2, 3, 4, 5. Something like this. And then I say, okay, let us draw the same picture, but use different units of measurement for our variables. Use different units. Let us now measure age in years and duration in seconds. Um, okay, we see that in this case, duration and age both measure some time, but of course we understand that they are quite different, and we should use different units of measure to measure them. But it is also possible that here on this axis we have not duration, but I don't know, some frequency or some any other thing that is measured in completely different unit. It can be measured in kilograms, in I don't know, in some abstract scale from 1 to 100, anything you wish. So if I will use different units, what happens with my picture? So now picture will look like the following. If I use numbers, okay, let me. This is 1 and this is 1, and then my picture will look like 2 points here and 2 points here, something like this. This is the same data. Basically, this is the same picture, but I just used different units of measure. And let me again enumerate my numbers: 1, 4, 2, 3. How would you cluster? How would you cluster this these observations now? Hmm? So just by looking at this picture, you have to choose probably this cluster and this cluster. And you see that the result of this clustering is completely different. But the data is the same. What is different is just usage of units of measure, because this change in units of measure changed the way how we measure difference between 2 points. If we measure distances here, we measure this duration in milliseconds. So points look to be very far from each other, if they have even small difference in their duration. And we measure age in centuries. So even people whose ages are, for example, 50 years and 100 years, looks to be very close to each other. This is an unavoidable problem because there are no any canonical way to define distances in these spaces. So we see that the result of our clustering is different, and this difference is due to usage of different units of measurement. And this shows that the usage of appropriate ways to measure distances is very important in solving these clustering problems. So let us proceed. Now let me discuss a little bit some ways to define distances. How to define distances. If you have just numerical values, if x1, x2, and so on, some numerical values, numerical variables, and I have 2 points, then how can I define distance between these points? For example, I have 2 points, and this point is x1, x2, and I have another point, x1 prime, x2 prime. How to find distance between these 2 points, just in ordinary sense. So distance between x1, x2, x1 prime, x2 prime. Yes, we can use Pythagorean theorem. And what is the formula? So we have x1 here and x1 prime here. So this distance is x1 prime minus x1. And the same here. We have x2 here, x2 prime here. So this distance is x2 prime minus x2. And how to find this distance? Actually, we have right triangle, this triangle. And due to Pythagorean theorem, we know that this thing, this is hypotenuse, and it is a square root of sum of squares of this thing and this thing. So this distance is a square root of x1 prime minus x1 squared plus x2 prime minus x2 squared. So this thing is called Euclidean distance. I wrote this formula for two-dimensional case when you have just 2 variables for your data, but a similar formula can be written in general case. So x1 prime minus x1 squared, xn prime minus xn, okay, xd. Something like this. And this is the usual distance that is usually that can be used if you have this numeric data. You see that this distance, if you change the scale of these variables, this distance will be changed in some non-trivial way. So, for example, if I rescale horizontal axis, then it will give me different formula here. So the units of measurement, the scaling of axis is important. And so basically we can define Euclidean distance in different ways just by rescaling the data. A usual way to standardize our data is to rescale them. So sometimes we can rescale data in such a way that, for example, if we have some variable x, we replace it to x divided by standard deviation of x. So we make standard deviation of each variable to be just fixed. And then apply Euclidean distance. This is a one way to avoid arbitrary choices of units of measurement. We just, in a sense, we just measure our values relatively to standard deviation of the corresponding values. So this is one possible ways to avoid arbitrary choices here. But this is not the only possible way to measure distances between points. For example, another possible measure is the following. Assume that you have 2 points. Again, I have x1 here or x2 here, and x1 prime here, x2 prime here. And I can consider the following distance. Distance between 2 points, x and x prime, is so I just measure this distance and add it to this distance. So this is also a correct way to define distance. It is a little bit unusual to measure distance in this way, but mathematically it is one of the possible ways to correctly define distance between points. For this distance, Pythagorean theorem doesn't work because in this case, this distance is just a sum of this and this thing. This distance is called Manhattan distance sometimes. Can you guess why it is called Manhattan distance?
Well, actually, I know it's called so because of the streets on Manhattan Island.
Yes.
So if you have to get to the point, you have to go not straight there, but turn right, left, something. No, yeah, something like this.
Yes. If you have a grid that is consists of streets and avenues, and you have to go from one point to another point, from here to here. Actually, you can go like this, or like this, or like this, but or like this. But whatever path you choose, the length of this path will be the same, and it will be equal to this plus this. So in a sense, this is a reasonable distance if we allow ourselves to move only horizontally and vertically. And it doesn't matter which path we choose, the result will be the same. So this is another way to measure distances. Actually, there are a lot of some other ways to do it. I just show you that distances can be defined in different ways. It is an interesting topic on how to measure distance if your observations have some categorical variables. So if, for example, x1 and x2, okay, if x1 is categorical variable, how would you measure distance between just categorical variables? Actually, if you don't know anything about these categories, probably the only possible way to define distance reasonably is the following. You say that if two observations have the same value of this categorical variable, then distance is 0. And 1 if they have different categorical values. So it is also a way to define distance, not very informative. But anyway, if you include some categorical variables, then measuring distances become a bit complicated. If you have several categorical variables, again, you have to define in some way how would you aggregate distances that are given by each categorical variable. This can be done in different ways. But so it can be complicated, and there are no obvious choices. You have to think about your problem and think which way to measure these distances will be the best one, or try to use different ways. But anyway, assume that we can define some distances in our set, and we want to make some clusters. Then we need to define some clustering algorithms. Let us discuss a couple of them. Actually, there are a lot of clustering algorithms, but I will discuss probably the most popular. And first is k-means. And in k-means algorithm, we need some points, some observations, and we do the following thing. Assume that we have two-dimensional space, so we have just two variables, and we have some points. Something like this. And then we do the following steps. First, we have to define number of clusters that we are looking for. Define k number of clusters.
And if I have no like idea how many clusters there is going to be, what should I do?
Well, you can try different ways, the different number case, and see what happens. Actually, there are some ways to measure how good your clusterization, so you can compare the results. Most clustering algorithms demand that you define either number of clusters or define some other values that that affects the number of clusters. So basically, it is not possible to say that, okay, that we definitely have two clusters. You cannot say this just from the data. Okay, then you can do the following thing. You have two steps, and actually, initially you just pick in some way, probably randomly, centers of clusters. They are called centroids. So it is possible that you just put some random points in your space. For example, I will put some point here, some point here, and some point here. Then you repeat two steps. First step, assign each observation to the nearest centroid. So for example, this observation will be assigned to right centroid as well as this observation, and these observations will be assigned to this green cross, and these observations will be assigned to this cross, and basically you have you can draw the following picture. To test which observations will be assigned to which centroid, we can draw these perpendicular lines. I just consider a segment that connects two centroids, and I draw some perpendicular lines. And these perpendicular lines will show me some regions into which centroid will split the space. So all these points will be assigned to this centroid, and all these points will be assigned to this centroid, and these points will be assigned to this centroid. So I have this assignment. Every point is just assigned to the nearest centroid. And then we have step 2. Now I have centroid, and I have some points that belong to this centroid. On the second step, yes. So on the first step, so initially we just pick these centroids in some way, for example, randomly. Then we assign points to these centroids. Each centroid corresponds to one cluster. Then on the next step, we will move these centroids in such a way that centroid is actually a center of the corresponding cluster. So for example, I will move for example, I will move this green centroid. I will move it somewhere here. Because it makes more sense. it is more in the center of the corresponding cluster. And I will move this point probably. Okay, probably this point is already located just near the center of the corresponding cluster. And this point also. So I move each centroid to the center. Okay, I can say center of mass of each cluster. I probably created not so good picture because here on the second step, more or less nothing changes. Let me draw a bit different picture for which these changes will be more obvious. Assume I have only 2 points. One point is here and another point is here. And then after the first step, something like this. And after the first step, I will do the following assignment. So the splitting line is here. So these points belong to red centroid, and these points belong to green centroid. And on the second step, I will move my green centroid to this point, and I will move my red centroid to this point. And then we can continue. For example, I will get I try to draw the same points. And now I get green centroid here and red centroids here. What happens next? Now I have to repeat these two steps. Repeat 1 and 2. Until there are no changes. So what happens on the next step? Which points will be assigned to green cluster and which points will be assigned to red cluster?
1, 2, 3, 6 are green.
1, 2, 3, 6 are green, right?
And 4, 5
so we have
are red.
We have these things, and we have this thing. So you see that in this case, picture changed from this to this. We have different assignment, and then we have again to repeat step 1. What happens next? So how we will move our clusters? For example, what can you say about this this red cluster? Where will we move it? So we have to move it in the center of the corresponding points. And if we have only 2 points, the center is just a center of the corresponding segment. So I will move this red thing here. And I will move this. Okay, I think that this green point is okay. I have to move this green point a little bit in this direction, because previously this green point were center of these 3 points, but now this point is added, so it will be shifted a little bit in this direction. And then I will get the following picture. Again, I will get 4 points here and 2 points here. I get something like this. And what happens on the next step?
We will get the same groups.
Mm-hmm.
And this means that we are lucky ones and we got the right result.
Actually, it means that our algorithm stops. It doesn't mean that we obtained the best possible clustering, but at least it means that our algorithm stops. We have here points, and we have here points, and we understand that if we will repeat the same steps, nothing will change. No, we don't need to have a point in the center of cluster. Yeah, center of cluster is just some abstract point, just some abstract center. It doesn't. We don't have to have an observation with these values. Even the first centroid can be none of our points, but usually people use algorithm that chooses some of your observations as initial centroids. But basically, it is not needed formally from the algorithm. Okay, so you see that in this case, for this picture, we get a reasonable result. We get this clustering, where this is one cluster and this is another cluster. And basically, this is what we probably expected to get from this picture. But it is not necessarily the case, because it is possible that different initial choice of centroids will lead you to different clustering. For example, assume that I have something like this. I have 2 points here and 2 points here. This is similar to what I plotted previously. And let me assume that I have some centroid here, and another centroid is here. Then my first assignment will be like I will put these 2 points here to the red cluster, and these 2 points to green cluster. And then on the second step, I will move this point here and this point and this point here. And then picture stabilizes. So I will get this clustering at the end. But let me assume that I have a bit different initial conditions. The data is the same. but for example, we have this clustering. We have these centroids. What happens next? What happens next in this case? How your points will be assigned to centroids and what happens on the next step? Yeah, we'll have vertical divide as Sarah says. And you see that in this case, these 2 points will be assigned to green centroid, and these 2 points will be assigned to red centroid. And on the next step, I will move this center here and this center here, and that's all. And so we see that here we have one clustering, and here we have different clustering, and it depends on the initial condition. So on the initial choice of centroids. So what people usually do, they do the same clustering algorithms a lot of times and choose every time different random initial clustering, initial centers of clusters, initial centroids, and then they compare the result by comparing sizes of clusters. So, for example, if we compare this picture and this picture, we would say that in this case clusters are more compact because these distances are smaller than these distances. So we can say that this clustering is better than this clustering and just stick with this result. And this is what clustering algorithms usually do. Are there any questions about this part, about k-means?
If we repeat this algorithm a lot of times, will we get some more or less stable model? So for example, out of 100 times, my algorithm, don't know, 80 times decided that I have some clusters.
You can, well, you can do it. So basically, you can look at probably, I don't know, is it implemented or not, but probably you can try to estimate how stable your clusters are. Yes, actually, what you can do is the following. You can remove random. You can remove some points from your initial sample. Not too much points, but you can remove some of them. And after that, you can repeat this clustering. And then you can see, is it true that your clusters will change dramatically? And if they are more or less the same as previously, if there is large intersection between new clusters and previous clusters, then probably it means that your clusters are robust, are stable. It means that if you had a little bit different data, but similar to that you really have, you will get more or less the same clusters. But if you have a dramatically different picture, then you probably cannot rely on the clusters that you created with your algorithms because it is too sensitive to small changes in your data. So this sounds to be rather reasonable. Randomization of initial places of clustering is usually done in the way that you just do it a lot of times, but you choose the best clustering according to these distances. So if you really want to test your clusters, the stability of your clusters, then it is reasonable to create a new data set from your data set by throwing away some elements, or procedure that is known as bootstrap, when you create a new data set from your existing data set just by picking of your elements with replacement, and then apply your clustering algorithms to this new data set. And you can do it a lot of times and see how stable your clusters are. So yes, this is reasonable.
Okay, and what is some data? How much of the data can I remove?
Actually, in most of cases, in these algorithms, people use a procedure that is called bootstrap. Actually, it is important procedure, and let us discuss it a little bit. The bootstrap is a way to get new data from existing data. And this is useful procedure if you want to test how reliable your conclusions that you obtained by analyzing of your data. What Bootstrap do? Let us assume that I have some data points. So I can draw it as a table. And every row of this table is a data point. So it is your observation. And this is my initial data set. And then I can create new data set by the following procedure. This is sampling with replacement. What is sampling with replacement? I just I get this initial data, and I pick one observation from this data randomly. For example, this observation, and I put it to the first place in my new data set. So this is my new observation. And then I do the same thing the number of times that, assume that I have here, for example, n observations. Then I will repeat this procedure n times. So I want to make n observations here, the same number of observations in my new data set as in the initial data set. And during this sampling, it is possible that I pick the same observation twice, or 3 times, or 4 times. At any time, every time when I want to add a new observation here, I just look one observation from here randomly. And I do not take into account the fact that I already picked, for example, this observation. So it is possible that my new data set is created in the following way. For example, I have, this is my second observation. This is my third observation. This is my fourth observation, and so on. And it is possible that some observations here are so unlucky that they are not chosen to be included to the new data set. This is okay. some of them will just remain not used. And with this procedure, you create a new data set that is, in a sense, statistically similar to the initial data set. But it is different. You don't have some observations. Some observations were taken twice or 3 times. And so then you can apply the same algorithm, for example, the same clustering algorithm, to this data set and see, do you have any significant difference between the results. So this is important procedure. And this can be done to test how good is your clustering, how stable it is. Okay.
I have a question about clustering. Could you please tell me, like, for what purposes can we use it? I mean, like, if I have a hypothesis that there are, I don't know, 3 clusters in my data, and I do this clustering, does it prove something or not?
Well, it usually don't prove, well, if you have a hypothesis that you have 3 clusters and then you run these algorithms, it will give you 3 clusters in any case. And so in a sense, it doesn't prove anything. But sometimes it is useful just for some observational purposes. So if you believe that there are 3 clusters, but you don't know which observations belong to each cluster, then you can do this clustering and just get some result. Sometimes it is useful during some kind of pre-processing work when you believe that you want to encode your data with some. This can be seen as a kind of dimensionality reduction algorithm. When you have some multidimensional data, but you want to replace this multidimensional rows with something very simple, like just one categorical value, just value that this data can be that this data point belongs to some cluster number 1, cluster number 2, cluster number 3. Sometimes this allows you to reveal some structure in your data that is not obviously seen. And for example, this allows you to, I don't know, create new hypotheses about your processes. So sometimes you just can say, okay, I see that it is okay. It is possible that sometimes you apply this clustering algorithm, and you get a result that this, and this observation are in the same cluster, and sometimes you can interpret it in some way. So it means that they are close to each other, more to some elements in some other cluster. I think we will discuss some examples during the exercises. Okay. Other questions? Mm-hmm. So let us proceed to another algorithm. This is called hierarchical clustering. And hierarchical clustering actually is a nice thing, because it gives you not just some predefined number of clusters, but some kind of hierarchy. It says that some observations are close to each other, some other are not so close to each other, and it gives you a way to look at your data on different levels of of scales, on different scales. Let me give you an example. I will discuss so-called bottom-up or agglomerative hierarchical clustering, and it works in the following way. Let me assume that I have some data points. I have something like this. So how many clusters do you see? Just your guesses, your intuition.
2 or 3.
2 or 3, yes. So both answers are in a sense correct, because we can say that we see just 2 clusters, this cluster and this cluster. But we also can say that we actually have 3 clusters. This cluster and this thing can be subdivided into 2 clusters, here and here. And actually, agglomerative clustering gives you both of these results. And let us see how it works. First, we begin with the first step when every point is inside each own cluster. So initially we have as many clusters as points we have. Every point is a kind of individual point that lives in its own cluster and is not united with any other clusters. And on the second step, we choose the points that are that have the smallest distance between them. In this case, it can be these 2 points. And we unite these points into another cluster of the second level. And then we continue. For example, on the next step, we can unite these 2 clusters, these 2 points. And sometimes we can say that we have to unite, for example, this cluster and this cluster. So we can merge different clusters. We have to define how to measure distance between clusters, but after we did it, we just do a very simple thing. Every time we get 2 clusters that such that the distance between these clusters is the smallest, and we consider and we merge these 2 clusters into a new cluster of the larger size. So we can continue like then we merge these 2 points, then we merge this cluster, then we merge this cluster, and finally we merge this cluster. The choice of colors does not mean anything. I just like colorful pictures. And finally, we will unite these 2 clusters and we will get one large cluster like this one. So this is how our algorithm works. And now you see that it can give you different results depending on how many clusters do you want. If you want 2 clusters, it gives you 2 clusters. It says no problem. You just pick this cluster and this cluster. And if you want 3 clusters, it also can give you 3 clusters. Just these 3 clusters. And so on. Actually, you can define how many clusters do you want. Or you can define the distance that you're interested in. and get this clustering. Also, it provides information about which clusters are united to which. So we can draw a picture that is called a dendrogram. And this picture looks like the following. We have points here. These points correspond to our initial data points. And then we unite them. For example, this, some points here. Then we can unite these 3 points. We can unite these 3 points. Then, for example, we can unite these 3 points. And then this, and finally this. So you will get a picture like this. And it is also possible to interpret on this dendrogram. It is also possible to interpret this height. So, for example, if you see that these 2 points are more or less on the same height, it means that when you increased the distance that on which you unite your clusters, then more or less these 2 clusters were united on the same level. It means that the distance between these 2 clusters is more or less the same as distance between these 2 clusters. And if you have points on different levels, it means that the corresponding difference in distances is large. So you can use this dendrogram to uncover some hierarchical structure from your data, from your points. And to finally define this agglomerative clustering algorithm, we have to define how to measure difference distance between 2 clusters, because initially we have just distance between points, and it is possible to measure distance between clusters in different ways. For example, assume that we have some large cluster here, and we have some smaller cluster here. And we already know that this is one cluster and this is another cluster. And assume that you have some point here in between. Assume that I have this point, for example, here. To which cluster will you append this point? How do you think?
Good question.
So we can append it either to the left cluster or to the right cluster, which
so
seems.
The criterion is the distance with respect to the centroid or not?
Yeah, actually we can measure distance between this point and this cluster in different ways. For example, Paulina suggests to append this point to this cluster. And this is reasonable if we measure distance between this point and this cluster by measuring the smallest distance here. In this case, this distance is smaller than this distance, or this distance. But we can measure distance between this point and clusters in different way. For example, we can find average of all distances to all points here and all points here. Or we can measure distance between this point and center of this cluster. And if we measure distance between this point and center of this cluster, and distance between this point and center of this cluster, probably this distance can be smaller than this distance, just because this cluster is smaller. For example, let us assume that we have something like this. This is one cluster. This is our point, and this is another cluster. Again, we have the same problem. How we measure these distances? And actually, it is possible to do it in different ways. Measure distance between two clusters. For example, minimum distance. Average distance, maximum distance, and distance between centroids. So everything is theoretically possible, and it will give you slightly different results. Again, you can think about your clusters, about your geometry, and choose which one to use, or just use default. I think that default in R is var distance that probably is this minimum, but I'm not sure. I have to consult the documentation. But anyway, this is one of the parameters that can be tweaked in your clustering algorithms. Other than these parameters, this algorithm work pretty straightforward. Just unite, 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 and then get this thing. So this is the results. Are there any questions so far?
I have a question. So, for example, we clustering somehow our data, and then in one variant of this clustering, we get some significant result. But when we clustering our data slightly in slightly another way, we don't have this result. Can you somehow comment it?
Well, you probably have to report both results, and you probably have to discuss why do you believe that the result of one algorithm is better than the result of another algorithm. So I think that there are no any universal answers here. Again, basically, this clustering thing is it is not very well posed. It is not very clear what to do. It just says, okay, we have some data, cluster it somehow. And sometimes if you have some understanding of their underlying algorithm and you have different results, you can probably explain why you have this different result, if these results are really different and if it is important for your research. Basically, clustering is not very strict method. I mean that if you do some regressions or you do some statistical tests, you have some hypothesis and you can test this hypothesis in some way, and you get some definitive result that your hypotheses are either you have evidence for your hypothesis or not. In clustering, you just have some clustering, and now everything goes to your interpretation, and so there are much less definiteness in the result of clustering. But sometimes it is useful, not always, but sometimes you need it. Let me show you a picture from scikit-learn library. No, we don't need Wikipedia. I like this picture because it shows us how different the result of clustering can be. So okay, I don't want to download. Let us make a 10 minutes break, and then I hope that it will be downloaded in 10 minutes. So 10 minutes break. So let us consider this data set. I will put it to chat. So in this data set, we have different languages, and we have some words that um, so this is this so-called words that are based on the Swedish list, and it is possible that two words coincide with each other in different languages. So we can use this as a way to measure distances between languages. And actually, I will just consider these zeros and ones as some characteristics of these languages. And now I want to apply different algorithms. I want to cluster these languages. Actually, we have 3 real languages and 1 column that is called outlier. It is added just for the sake of our classes. So in this outlier, we have all zeros. This is just artificially added column. And now, if I want to create to apply some clustering algorithms to this data, I can do it in different ways. Okay, if I have only this kind of data, I think it is better to use hierarchical clustering because it is not very easy to visualize these points in so large space. So basically in this table, our languages are written in columns, but I want my observations to be written by rows, so I can transpose this table. Let me select only this part. So this is from 3 to 1, 2, 3, 4, 5, 6. So I get this part of my data, and then I can transpose data frame. This can be done with this T function. And it just creates me a new table such that rows of this table are columns of the previous table. And now let us assume that I want to use hierarchical clustering. Yes, just a second. So if we want to use hierarchical clustering, we have to create the so-called distance matrix from these points. And we have to feed these distance matrix to hierarchical clustering algorithm. Actually, the only thing that we have to know to use hierarchical clustering are distances between points, because everything else can be calculated. And this is different, for example, if we compare it with k-means. In k-means we have to know the actual values of all elements of your data, of all variables for each observation. But for hierarchical clustering, you just have to know different distances between them. And we can use function dist. So let me denote it in some way. And then I can use function dist. And this function creates a distance matrix that finds distances between my objects, between rows of my table. Actually, it can use different methods. So Euclidean maximum is just find maximum difference between points. Manhattan that we discussed. I don't know what is Canberra. I don't know what is binary, and Minkowski, it is a version of Euclidean, but a little bit different. But let us now stick just with Euclidean. This is default. But just to see what happens if I will use maximum. How do you think what will be the result for this method maximum? Actually, I don't know. I just have a guess. If I use as a distance between two rows, I use maximum of difference between elements of these rows.
Displays to me something like binary.
Yes, but what will we get in this matrix? Yeah, this is just 1, 1, 1, 1. So you see that in this case, this method is not very informative because it just says that maximum distances between all our rows is just 1, because this is what we have. Do you understand why we have this result for this data? So just to be sure. You see that our rows are just consist of zeros and ones. So if I will use maximum difference between this row and this row, I have to find difference between this one and this one. Difference between this one and this 0, it will be 1. Here it will be 0, here it will be 1, and so on. And then I get maximum of these distances for each element. So maximum will be also 1. And it is not very informative. Let us stick with Euclidean. Okay, we can use Manhattan just to see what happens. Here in Manhattan metric, you see that everything is integer, again, because our result, our initial values are integer. And we just have some summation here. So if you have two rows that consist of zeros and ones, how can you characterize what is Manhattan distance between these rows? How can you describe it? For example, what is Manhattan distance between these rows? What is Manhattan distance between these rows?
There is no distance, like 0, no?
If we have 0 distance, then it means that two rows coincide with each other. If 0 is 0, then it means that objects are just the same object.
Maybe 3.
3, why 3?
We have 3 places where we have different things.
Yes, exactly. So for binary sequences of Manhattan distance is just the number of places for which corresponding values are different. So we have difference here, we have difference here, and difference here. So this difference is 3. And so if we use Manhattan distance here, we will get only integer numbers. Actually, in this case, Manhattan distance is also called Hamming distance. Number of positions where sequences. Okay, let us use just Euclidean distance. And let us try to use hierarchical clustering. And I will feed my.
How can I understand these results? I mean, for example, if, I don't know, if we write Manhattan, so the result between Lithuanian and Lithuanian outlier and, I don't know, Latvian outlier is much higher than by Euclidean distance. What does it mean, and how should I understand all of that?
So if we compare these metrics and these metrics, we see that there is relative difference between. Okay, we see that here Lithuanian is close to outlier, but here they are
Yes.
far from each other.
Yes.
Okay, how can we interpret it? Let us look at our Lithuanian. Actually, this number 11 is also pretty large because here you see that here distances are like 10 or 11, and here they are about 100 or so. So I think that this number and this number are more or less the same. For example, we can divide these distances by a number of so actually this distance is itself larger, because here when we do this Euclidean distance, we find square root of something, of some sum, and here we don't have this square root. So this is pretty natural that these numbers will be smaller than these numbers. So I don't see much difference between these two numbers. Probably I see some difference between these numbers. So here distance is relatively small if we compare it with this number. If I get this old Prussian, so we have a lot of zeros here, but it seems that in Euclidean distance, these values of 1 are counted with, in a sense, larger weight. Why does it work like this? So I have some square root here.
So my question actually is that if I'm, I don't know, writing an article and choosing the method, how should I decide? Should I use, I don't know, Manhattan or Canberra or something? Like, the results are going to be the same or not? And if not, how to choose which one is better?
Well, I don't have universal answer here, as usual. If you don't know, you can just stick with default values, like Euclidean distance. But actually, I cannot provide some good example when Manhattan distance is better than Euclidean. Probably in some cases this can be the case, but I cannot imagine it. But basically, you can use Euclidean just because it is default. So unfortunately, there is no universal ways to choose one over another. Okay, let us use Euclidean now, and I use this clusterization. Now let us use this clustering. So in this case, we just use only, we have only 4 objects, and we will cluster these 4 objects. Let us draw something. Let us draw Dendrogram. Actually, here you see that this algorithm, first of all, it united this old Prussian and this outlier column. Actually, this is reasonable to expect because this distance is the smallest. And then it united Latvian and Lithuanian. That is also reasonable. And on the last step, it united this cluster and this cluster. So this is our dendrogram. It is not very complicated in this case when we have only 4 observations, and we see that these results are in agreement with this result. Actually not result, but just our intuition about this table. Another way to analyze these clusters are the following. We can this function. So we can say that I want to cut my cluster, my dendrogram at some level, such that I will get the desired number of clusters. For example, I cut this diagram now, and I asked for 3 clusters, and I get 3 clusters. In one cluster, we have Old Prussian and outlier. And we also have distant clusters for Latvian and Lithuanian. Okay. So after that, you can use this this subdivision into some other tasks. Here I used I asked to give me 2 clusters, and I see 2 clusters: Old Prussian and outlier, and Latvian and Lithuanian. Now let us consider another data set. So we have some information about some acoustic properties of speech of different speakers. Some of them are heterosexuals, some homosexuals, and we have some information about their age. And now we can try to find some clusters in their acoustic information. And to do so, let us consider only appropriate columns. For example, I want this, and these columns. So 1, 2, 3, 4, 5. I also want to keep my names of the speaker here. So let us put these names of speaker as the name of row. So and then we can apply some, for example, Kamin's algorithm or hierarchical clustering to this data set. Let us try with Kamin's. So it is already implemented in R, and we have to provide our data. And then we have to provide the number of clusters. For example, I want to consider 2 clusters. Here is the result of my clustering. So it gives information which value is, which observation is assigned to which cluster. So I have 2 clusters, 1 and 2. And it also gives information about the corresponding centroids. So these are centroid of my clusters. And here it gives information about sum of squares of distances inside each cluster. So I consider every pair of points such that this pair of points is within the same cluster, and find the corresponding sum of square of their distance. And it gives me this value. It says that this sum of squares within cluster is within each cluster, and this is sum of squares between clusters. And it says that this between sum of squares divided by total sum of squares is 65%. Well, it is not clear how to interpret this number alone, but the larger this number, the worse our clustering, because this is distance between different clusters. If this number is large, it means that no, the larger the better. If this number is large, then it means that clustering is good. Sorry. So we can draw something about this clusterization. For example, we can draw a picture. Okay, probably we have more columns to consider. Let me see. First format. Okay, no, only first format here. Anyway, we can draw, for example, picture. Let us just use 2 columns. For example, this column and this column. And I can plot something like this. So I need my this clustering. I want to add this clustering vector to my data frame. I have this variable here, so I can just say that let me use tidyverse library. let me add clusters here. So we see how it is clustered. These points are in one cluster and these points are in another cluster. Let me use different scale for clusters. So I have to convert. Currently, this cluster is just numeric value, but we understand that it is in fact categorical. So I have to convert it into factor. So I have to add S factor here. And now I have a nice picture.
I didn't get the idea what this S factor do.
This S factor converts our column into factor. So let me show you. By default, this thing is a numeric vector. If I ask what is, yeah, it says that it is just a vector of integers. But I want this thing to be not numeric things, but just some kind of categorical variable. So I convert it using this S factor. Now this is categorical variables, variable with two levels, 1 and 2. And then ggplot understands that this is categorical variable, not numeric, but categorical. And so it draws it in this way. So it says that for each value of this category, we have, for each category, for each factor level, it creates its own color. And we have this picture. If I remove this as factor, it just thinks that this variable is some numeric variable that changes from 1 to 2. And it creates different visual representation of this variable. It assumes that it is some variable that on some continuous scale, on some numeric scale. So this is just a way to say to R that this column will be categorical. Okay. So we basically see that we have some result here. Probably this clustering is more or less natural, but I'm not sure. We can look at different values. For example, we can look not using these columns, but other columns. Note that my k-means used information in all 4 columns, but I cannot draw pictures in 4 columns. So I can do it in this way. You can try to draw the corresponding picture with different columns.
Can you let us look through the code, because I have a mistake and I don't understand
Okay, okay, where should I scroll?
I don't know why, but CL is not object CL not found. Yeah, I did it.
It should work because in this line we create variable CL and put the result of our k-means.
Maybe we had some library.
Well, I only use this tidyverse, but well, it should work now. Can you send me a screenshot?
I will try one more time and I
Mhm.
will send it to
Okay, actually we can plot another picture. Let me assume that I want to plot this picture, but not use these coordinates, but instead use coordinates that are obtained with principal component analysis. So I want to reduce dimensionality of my data and put it in this way. So I can do it. I need PR comp. Again, I will use the same date numeric. And then I can use this function predict to find components of each. Okay. I can use this function, but also probably I can just use fortify like we did it previously, ggfortify. Yes. If I want to plot a picture in my principal components axis, and I want to color these points with the corresponding clusters, I can use this thing probably. ggplot. Can I do it in this way? No. Just a second. It should, but okay. So this is the result for in the axis PC1 and PC2. So again, we see that there is some more or less natural clustering into two groups because we have large distance here.
Why this picture has changed? I'm sorry, I did not get the idea why this picture changed so much.
Well, I used different coordinates. Initially here, I plotted this picture using coordinates these two. So initially my data are 4-dimensional. I have 4 columns. And to make this plot, I have to reduce the dimensionality for two dimensions. And here I just used two columns from my data. This is average F naught, and this is F naught range. And in this case, I use principal component analysis to get my coordinates. So this picture actually can be a rotated version of this picture, or maybe in some ways rescaled version. Basically, let us add initial coordinates to see how it works. So I want to add loadings. So basically, we can say that this picture is a rotated version of this picture, because you see that here our coordinate F naught range is horizontal, more or less horizontal, and this is more or less vertical. So you see here that this is vice versa. Here F naught range is vertical. So this is basically the same picture, but rotated. And
Okay, thank you. But I have some problems. It doesn't work, and it's written that object of type PeerComp is not supported by autoplot. Comp.numeric.
well, we did the same thing on the previous lesson.
Okay, I see. Thank you. Sorry for interrupting.
Okay, so here I just in this picture I just used these columns, and I added to my initial data set. I added a new column, and in this column we have information about to which cluster each object is assigned. So we can just look at this new data frame. And for example, this is my first row, and it is assigned to cluster number 2, and this is called cluster number 1, and so on. And here, the same values of clusters. And here I just use these clustering numbers as a way to distinguish my points using color. And so I get this picture. And in this picture, actually, these two pictures are very close to each other because it appears that in my principal component analysis, this is actually a coincidence. These two variables aligned with my two first principal component analysis in a good way. So I get this picture, which is pretty close to this one, just after rotation. Okay, are there any questions here? Okay, then let me ask you a question. Use H class to get clusters. So we can apply H class to the same data, and we have to do it just like we tried previously here. So we have to create distance object and feed this distance object to function H class. Let us use Euclidean metric as previously, and I just want to compare the results. Will I get different clusters or the same clusters? So you just need to do the same thing as here. So we can draw the same picture. For example, draw picture in like above for variables. These two variables. So so the same thing. Anybody succeeded? If you have any questions, any problems, just let me know.
Can you show the code with HClust?
Mhm.
Я запуталась.
Так. Можете что-нибудь прислать? Код, скриншот, сообщение об ошибке. В принципе, нужно сделать то же самое, что вот здесь. Мгм.
And then we should plot it, yeah?
Мгм. М.
And now we work with the second data frame.
Yes. Mm-hmm. Значит, okay. H-class object contains all the hierarchy, and to get actually two clusters, you have to use this function that returns your vector that shows you to which cluster each object is assigned.
I have some result, but I cannot comment it. So it is just a picture with yellow and blue and white.
Does it look similar to the previous picture? Can you just show it?
I can share screen if you would like.
Okay. Wow. Wow. No, it seems to be different different picture. It is not what we want now. Now, you use autoplot to draw pictures for principal component analysis, but my problem currently is more simple. I want you to plot the same picture as here. You see that we don't have autoplot here. I just use ggplot to draw. I actually get my initial data frame. I add a new column with information about which cluster to which cluster each row belongs, and then I plot this data frame using jump point, and I use these variables as my axis. I just use this color that is equals to cluster to distinguish between two clusters. So you have to use this kind of function, this line. Do you understand what this line do? Every part of it? It'd probably be better if I split it into two parts. Probably I have to do it in this way. But here I used just cluster, just if I used k-means object, k-means clustering, and then it contains this information here. So this CL object in this example, it is a result of k-means clustering, and k-means clustering gives you this clusterization. But if you use hierarchical clustering, it doesn't give you clusterization automatically because it gives you hierarchy of different levels. And to get clusterization, you have to use this function cut3 that just cuts your dendrogram at some level to get the number of clusters that you specify here. We discussed that from hierarchical clustering, you can get as many clusters as you want. So here is just your request. You say, I need 2 clusters from this hierarchy, and it gives you the result. So here is your plan. Okay. Other questions?
May you check Telegram? I sent a screenshot.
Mm-hmm. 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 So let me try to do it by myself. I want to Mhm. So I will use clustering. I use hclust. I find distances between my data points. So I use dot numeric. We can see the result. So this is my dendrogram. It is not very informative for me because I don't know what these points means. But anyway, let us now we can use cut3. We have to specify a number of clusters. So we get this result of clusterization. And then I just put it to the same code here. So I should change here because instead of CL cluster will not work. You will get something like this. This is because this CL object now contains information about this hierarchy and does not contain any specific clusters. So to get clusters, I have to use this cut3. And then I just put it like this. Clusters and so this is the result of this cut3. And this is my final picture. And you see that this picture is very similar to the picture, this picture, despite the usage of different methods. So
Okay,
we
so
see
there is no difference which method to use. So there is no difference between methods we use.
Yes, at least here, at least for this data set. Actually, well, it is a good situation where because if we believe that there is some clusterization, then all good methods should result the same thing. So if you have some data, you apply different methods of analysis and get the same result. It is a good omen because it says that your results are robust to the choice of the method. So it is a good thing. But basically, in this clusterization, we can play, for example, with increasing of number of clusters. For example, I added one more cluster. You see this blue dot here. And I did it by adding this k equals to 3. And I can do the same thing with my k-means. I just have to change this number. And let us see the picture. You see that k-means get different 3 clusters. So it didn't put this point to its own cluster, but it added a new cluster here. I don't know why, but anyway, we have this result. So you see that it is also possible to get different results from different methods. This is what we have usually. So I think that that's all that I want to discuss today. Are there any questions?
I don't understand why. So you commented my mistake that Q3 so I don't understand it. I think I just missed it. Can you just repeat it?
Can you recall what mistake do you have?
I think we can speak Russian, no? Вы мне написали, что у меня Q3 не изменил объект КЛ, и я, видимо, что-то не понимаю.
Да,
Видимо,
ну
я что-то
смотрите,
пропустила. Ага.
вот смотрите, значит, вот эта штука,
Мгм.
она не меняет вот этот объект CL. Я вот здесь использую не CL, как раньше, а я использую то, что мне вот это K3 вернуло. Она
Всё, я
вернула
поняла.
мне значит, какой-то там вектор. И я вот этот вектор сюда подставляю. А у вас
Мгм.
здесь было написано что-то вроде KL, значит, доллар clusters,
Мгм.
и это как если бы Q3 поменяла CL и превратила его в такой объект, какой бывает, который commits возвращает. Но так не работает. Вообще в R объекты неизменяемы. То есть если вы вызываете какую-то функцию, передаете ей какой-то объект, этот объект не изменится. Скорее всего, то есть, скорее всего, все функции нужно использовать вот так. Функция чего-то вернула, вы сохранили это возвращенное в отдельную переменную, и дальше с этой переменной работаете.
Мгм.
Вот.
Спасибо,
Это там
теперь
принципиальное
понятно.
отличие, допустим, от питона. В питоне может такое быть, что вы переменную отдаете в функцию, и функция меняет эту переменную. Тут такого не бывает. Okay. Other questions? Okay, then that's all for today. If you feel that you need some consultation, you can put your name into the table that is shared in our chat, and we will discuss your projects. If you do not feel that you need consultation, but I will look at your project and I will feel that we need to discuss something, then I will let you know. So that's all for today.
And how long should be our proposal?
I think it can be just a kind of one page. Well, I do not impose any formal restrictions. After reading this proposal, I have to understand what is your problem, what you're investigating in your linguistic terms. Like I'm studying how this verb is changed when something changes or something like this. I have to understand what kind of statistical hypothesis do you test, like what I will count how many times this verb is used together with another verb, and I will compare this number with another number using, and I assume that they will be different, something like this. And then you have to discuss where did you get your data, where are you going to get your data. It can be some corpus study or some, probably you will do some survey, I don't know. And you have to specify which statistical tools will you use. Like I will use chi-squared test to test something and something, and I will use regression with the following variables, with the following dependent variables and the following independent variables, something like that. So If you can put it into just half a page, that's fine. If you need to write a couple of pages, that's also fine.
Should I, who's gonna read that? I mean, should I explain some, I don't know, linguistic ideas? For example,
Well, I will read it probably with Olga, but we will not assess any linguistic components because, for example, I don't know linguistics. It will be good if you explain, well, it should be understandable more or less by me, at least as possible.
okay.
Mhm.
Like as I see, we're gonna discuss it somehow after the proposals are sent. Is it?
Yes, yes. At least if it is needed. If I see, if you don't need it, and if I will read your proposal, and if I see that everything is perfect, then I can just say, okay, go on like this, and that's all. But most probably we will have some discussions with all participants. So we will just arrange some.
Okay, thank you.
Okay, then other questions? Okay, then that's all for today. Bye.
Thank you and bye.
Bye.